Welcome to Season 3 of Evolution in Controls. I'm your host, Tim Wilson. Thank you for joining us as we kick off another exciting season of motion control innovations, challenges, and solutions. We start by looking at mobile hydraulic systems. And the question is, what would you think if you could cut the size of one of the largest elements of that system in half? Reduce it by 50%. What if you could do so by abandoning standard design practices and simply optimize around a new design? Conventional design practices may follow standards that are neither the most efficient nor the most effective. Standard design practice uses the size of a reservoir to achieve deaeration of the hydraulic fluid. Imagine if deaeration happens not because of the size of the tank, but because of the return filter used. Deaeration happening in the filter and not the tank. This simple shift in approach can significantly reduce the size of the tank used. At the forefront of this advanced filter reservoir technology is our trusted vendor partner, HYDAC, whose innovative strategies meticulously analyze filter reservoir systems and optimize air removal. To help us dive into HYDAC's filter tank optimization strategy is Mr. Andrew Krajnik, System Integration Manager at HYDAC. Andrew, thank you for joining us today.
Happy to be here, Tim. Thanks for having me.
Well, let's start a little bit about yourself. How long have you been with HYDAC? How long have you been in the industry?
I've been with HYDAC for 7 years. Prior to that, I was with Caterpillar for 14 and a half. Started in heavy-duty piston pumps and motors and then moved over to the machine side, and now I've been in systems ever since.
Okay. System Integration Manager. What does that mean? What are you integrating together? Certain products?
Well, kind of any and all HYDAC products. HYDAC has a wide range of technologies in hydraulics, electronics, controls, and now some new e-mobility components. And our advanced systems team is focused on integrating, well, any and all of those technologies that might be applicable to a given OEM.
Well, we're here to talk about deaeration, and as you heard in my introduction, tank size and deaeration and maybe a filter technology. Let's start with some basic concepts. Why deaeration? Why do I need to deaerate the hydraulic fluid?
Well, air in oil is bad. It causes issues with the stiffness of the hydraulic system. So if there's a lot of air in the oil, the hydraulics don't behave the way you expect them to. And it also has impacts on the life of the oil and the life of the components in the system.
The components can be damaged because of the air
Yes.
in the system. So what is it about the size of the tank that causes the oil to be deaerated? Is it surface area, the volume of the tank? What is it?
It's mainly the volume of the tank. Bottom line is that the majority of tanks on the market today were designed using best practices and rules of thumb because everybody knows air in oil is bad. And previously, the only way to get air out of the oil was to just let the oil sit there so that the bubbles could rise to the surface. So you end up having to size your tank to allow dwell time for those bubbles to rise.
Settling time? Just the
Yes.
time for the oil to settle and let the air just come out of solution of the oil.
Yep, so for a certain amount of pump flow, I know I have to make the tank a certain size so that the oil hangs out in the tank for long enough for the bubbles to rise before it gets sucked up by the pump again.
How do the customers know how big a tank needs to be? We talk about standard rule of thumb, 3 times the flow rate of the oil. Those are standards, right? Do they always apply? Does it always need to be that?
Well, different industries kind of have converged on different solutions depending on how dynamic a machine is. You might see one particular machine has a different ratio than another, but by and large, it's best practices, rules of thumb, and carryover from previous designs. So they'll take a look at the previous design and just try not to change it too much. They might try to shrink the tank a little bit, but they don't want to get too aggressive because everybody knows air in oil is bad, and the way to get rid of it is to make your tank bigger.
So where does this process start? How do you, if you have somebody that wants to reduce their size of the tank, how does the process start?
So for us, we take a different approach. Rather than just relying on a best practice, we actually do a detailed simulation of the tank itself. So we're doing computational fluid dynamics, or CFD, where we are simulating the behavior of the oil in that tank at the flow rates that that tank actually sees. And we go even a step further and actually simulate the behavior of air bubbles in that system. So we can analyze a system and basically draw some conclusions about how good of a job that we would expect that system to do at removing air from the oil.
In my introduction, I talked about a filter that you're adding, and so you're putting a new component. Filters are not new to hydraulic systems, but there's something new about this filter you're talking about adding.
This filter in particular is designed in such a way to modify how that oil behaves as it's coming back into the tank. So there's a couple of things that the filter technology itself does that greatly improve its ability to deaerate the oil and allow us to make significant reductions in tank volume.
So a filter filters out dirt. Is it filtering the bubbles out also? Is that what it's doing, or is that not the right look at it?
No, it's not. It's still, the filter primarily is removing the dirt, right? But one of the things it's doing is we've essentially inverted the way that the filter works so that the entire surface of the filter becomes our return port. So we're drastically reducing velocities in the tank,
okay,
so that that oil doesn't tend to drag bubbles along with it. We are also keeping the return oil close to the surface of the fluid so that bubbles have a shorter distance to move. And then the final thing that we do is we have a bubble coalescing element to the filter that causes small bubbles to group together to form bigger bubbles, because bigger bubbles rise faster.
So you do computational flow dynamics. You do that for the existing system or the current system. Do you also do the modeling with this new filter element in it?
Yes, so we'll do the CFD on the baseline design, and then we'll employ the new filtration technology, help them design a new tank geometry, and we can do that same analysis on that so that we have an apples to apples comparison of how the old system would perform versus how the new system does.
All right, there are always going to be skeptical people. How do you prove to the skeptics that it's working? What do you do? You've got computer drawn pictures, CFD analysis of conventional and a new design. How do you prove it? How do you show it to them?
So we've done a lot of work in the lab to validate our simulation techniques. And then the other thing that we do, a very powerful tool, is we have a demo stand that has two tanks side by side with windows in them, standard filtration technology, new deaeration filtration technology. So you can actually see for yourself the behavior of the oil in that tank.
It's not the customer's tank or their particular shape of a tank, but it's two tanks and they're identical.
Well, not identical. They're undergoing identical flow profiles,
okay,
but the optimized tank is significantly smaller.
Ah.
In fact, we do have that demo stand out in our shop if you'd like to take a look.
Is that what this picture is?
Yeah, that's just a static image of that demo stand. We have that out in the shop. We can actually show that to you if you'd like to see it in person.
I want to see it. I want to see it. I'd like to see the difference between those and what you show the customers.
Absolutely. Let's go take a look.
Okay. All right, Andrew, we're here in the lab at HYDAC. Why don't you tell us what we've got here?
So this is just a demonstration stand to show the capabilities of our deaeration filtration technology. So we have two tanks here. One is a more traditionally designed tank with a typical just return filter. This one has our RFB deaeration filtration technology in it.
This tank is smaller than that one, though.
Yep.
This is what?
About 40% smaller than that one. And again, it's to demonstrate the difference in performance and, of course, showcase the ability to reduce tank volume once you're using a deaeration filter.
They both have a return filter.
Yes.
This is your RFB. This is
Correct.
The technology that we're talking about.
Yes, absolutely.
What do we have down here?
So underneath here we have basically two motors, two pumps. So these are running separate systems. We have VFDs running the motors, and we're going to run those through a flow profile. So when I hit the start button, basically both of these tanks are going to be seeing the exact same flows at the exact same time.
So I've got two electric motors, two pumps. They're the same size pumps.
Yes.
VFD controlled motors, and it's going to run a load profile on the motor.
Correct.
Correct? So both tanks are going to experience the same amount of flow, the exact same amount of flow.
Yes, and it's important to note that because once we hit the start button, what's happening inside these tanks is going to look drastically different, but I assure you at every given point in time, they are seeing the exact same flows.
Hit the button. Okay, I can see that you've got motion in one of the tanks. The motors are speeding up, slowing down. They're running a profile. Why do I have motion in one tank and not the other?
So one of the things that we're concerned with when we're looking at performance of a tank and its ability to de-aerate is the velocities of the oil in the system. And with a traditional tank, you end up with a fairly small return port for the amount of flow that's coming back. That results in very high velocities. High velocities do two things. First of all, when oil is moving fast, it tends to drag bubbles along with it, right? Those bubbles that are coming back to the tank, we want them to be able to float to the surface. The faster that oil is moving, the more they have a tendency to just follow the flow of the oil rather than floating to the surface.
So you're saying that because of the return filter in this tank and the different return filter here, both of these tanks are getting the same amount of flow.
Yes.
And I'm seeing, because of the differences, I'm seeing all of this fluid motion that's not happening here.
Right, so we have much higher velocities here. The other way that velocities hurt us is if you have high velocities at the surface of the fluid, it causes churning, and that's exactly what you're seeing on this tank here, is that we're actually frothing air into this oil because of the high velocities at the surface. Now, if we look at the RFB filter over here, we're doing something a little different. With a typical filter, the exterior of the filter element is the dirty side of the filter. So the oil flows around the outside of the filter, flows from out to in, and then it still has to exit through the end of that filter element. So even if you put the filter inside the tank, you still have very high velocities. With the RFB, we've literally turned that inside out. We call it in-to-out filtration. So now, with an RFB filter, the dirty side of the filter element is the interior of the element. So it's flowing from the interior to the exterior. And when we do that, by putting the filter inside of the tank, essentially the entire surface area of that filter, the entire exterior surface, has now become our return port, so we get very, very low fluid velocities, which is why you have to look closely to even tell that there's flow happening here.
I can see there's flow coming through the wire mesh. On this filter here, the oil is coming out from the bottom.
Yeah, it's coming out from the bottom, and then it's flowing over, and again, we get high velocities churning. That oil velocity is hitting off the bottom of the tank and then reflecting back.
So the oil is coming out of this filter all around it, top to bottom.
Yes. So that's the second portion of how this helps us. First of all, again, we want to slow those oil velocities down. We want to eliminate that churning at the surface and want to prevent that oil from dragging bubbles around. The other thing that we're doing here is we want to keep those bubbles as close to the surface as possible, right? That bubble has to float to the surface to be de-aerated. So we're actually returning a portion of our oil above the level of the fluid. So what's happening, we're getting that nice, calm oil cascade down the outside. So any bubbles that are here have a very short distance that they have to move to be able to float to the surface and be de-aerated.
So as I look through the oil, this still looks the same color as it did before you turned the button on, but that's white and cloudy now. That's all because of this filter element.
That's all the air that's building up in here. The other thing that you'll notice here is, look at these big bubbles, how quickly they rise to the surface. That cloudiness is caused by the tiny bubbles. And really what happens is, because of the physics of how bubbles behave, larger bubbles rise faster. So that's the third element of what we're doing with this filtration technology. You notice that metal mesh on the outside, that acts as a bubble coalescer. Again, bigger bubbles rise faster. That metal mesh is there to help little bubbles clump together to form bigger bubbles so that they de-aerate more quickly. So as long as we're running this machine, we can run this tank all day long, and it's going to stay crystal clear like this because it does such an effective job of removing air from the system.
If I hadn't seen it with my own eyes, I don't know that I would have believed it, although I understood what you were talking about. This is a very effective demo. Andrew, thank you so much.
Thank you, Tim.
All right, I'll admit, that was fascinating. I loved seeing the one side being still and the other side being chaotic and turbulent. I didn't expect that it was going to be like that. Do you get that reaction from customers?
Yeah, as you can imagine, it's a very powerful tool for us to really help drive home the value of this technology.
So you bring the customers in, you show it to them, they see the two demo tanks. At that point, are they convinced? Do you begin working with them then and redesign their tank?
Yeah, in general, at that point is when we really start talking details with the customer, is to say, hey, give us a model of your existing tank, we can do that analysis, and then we start working on our iterations of an optimized design for them.
All right, so you redesign the tank, you do your computational flow dynamics, you show them the demo, you redesign it, but the tank that they see is not the tank that they get. How do they know that it's working? I don't know how to be any more direct about it, but how do you prove it to them?
So I'm glad you asked that. That's actually the third phase of what we offer to our customers. We talked about that detailed CFD analysis. Yep. We've talked about the technology and why it works so well. The final thing that we do is we can actually test aeration levels in a machine while it's operating.
You put a window in the tank?
Well, we can, and we have. There have been customers that request that when we do the prototype tank, we put a window in it. But actually what really helps us is we have proprietary air content sensing technology. So what that does is it allows us to instrument up a machine and measure the air content in the machine while it's operating. So we'll start with the baseline tank. They'll send us a machine, or we'll bring our air content sensor to a customer site. We'll instrument the machine, and we run that machine through a typical work cycle. So we get baseline aeration data from the existing tank. Then when we put in the prototype tank, we do that same test. We do that exact same work cycle with the new tank so that we can actually compare apples to apples. What are the air levels in the oil while that machine is doing its typical operation?
But you're not actually trying to show with this measuring device, you're not actually trying to show a difference in aeration, because if the standard tank is de-aerating, you just want to show that it's doing as good a job, or maybe better, than the existing tank.
Yeah, the fact of the matter is that the majority of tanks out in the field don't have an aeration problem. They're just carrying around more oil than we need to. So we're taking a de-aeration filtration technology and applying it to a system, not because there's an existing air problem, but because we can significantly reduce the oil on board.
Okay, so now that's where it gets interesting for a customer. Do you have to dollarize the savings or the advantage of doing what you've done, or do they know it immediately?
I mean, it really starts to click once they see the demo, and once we start showing them how much smaller that tank is, it really starts to click. But we do help walk them through that value proposition, essentially taking a look at that system and saying, we're removing this many gallons of oil, which weighs this much and costs this much and takes up that much space, but then we're also simplifying the tank itself. This filtration technology lends itself to very simple prismatic tank design, so you don't have to do a lot of complex baffling. So not only are you reducing the material in your tank, you're also reducing the complexity of it as well.
The tank is cheaper to produce, not because it's just smaller, but because it's a more simple design.
Simpler as
There's
well.
not stuff inside it.
Exactly.
Well, what does the future look like? I mean, have you done this for one customer, 10 customers? How long have you been doing this?
So HYDAC's been doing this type of analysis and this type of filtration technology for about 10 years now, and we've done literally hundreds of these. And when I say hundreds, I don't mean we've just analyzed hundreds of tanks.
Hundreds of customers?
Hundreds of customers. Hundreds of customers where we have actually realized significant gains and put those new tanks into production.
So what does the future look like? If you've been doing this for a decade and you've dealt with hundreds of customers, what does the future look like? Is it just a more broad adoption of this? Is there technology that you can bring to bear to improve the design of your element?
Well, it's actually both of those. I mean, certainly broader adoption, right? There's a lot of people that aren't even aware that this technology exists, and we want to get it out in front of them because we can provide significant value in those applications. But of course, we don't like to stand still either. So we're always working on improving those technologies and adding new features to that same basic filtration technology to reduce the cost of the technology, as well as adding features to optimize it for unique types of systems.
Well, I'll be curious to see what the next 5 years, 3 years looks like. New technology, to see how the adoption. Let's have you come back in 3 or 4 years and talk to us about what the last 4 years have been like.
Absolutely.
You willing?
Sure.
All right. Andrew, thanks for joining us today.
Thanks for having me, Tim.
To learn more about HYDAC, their products, solutions, and markets, visit HYDAC.com. To learn more about Marel and their systems and solutions, visit Marel-Group.com. Don't forget to subscribe to Evolution in Controls on whatever platform you use for podcasts or on YouTube for a video version so you can be updated when we release new episodes. Thank you again for joining us today. I'm Tim Wilson, and remember, keep moving.